In the name of Almighty God, I am Master Sankoshi, and today I want to talk about nitric oxide and ammonia conversion in a dual bed monolithic reactor. This example illustrates the modeling of a dual bed reactor for exhaust gas treatment in a heavy duty diesel truck. The reactor consists of two monolithic beds placed in the series. In the first bed, selective catalytic reduction (SCR) of nitric oxide (NO) and NO2 with ammonia occurs. Downstream of this catalytic bed, an ammonia slip catalyst (RSC) is installed. The RSC bed converts the unreacted ammonia into nitrogen. In both beds, there are also undesired side reactions. The complex chemical kinetics is investigated in detail in analysis of NOx and ammonia conversion kinetics in a dual bed plug flow reactor from that study where a single monolith channel was modeled. It is clear that temperature plays a central role for the selectivity of the system. The current model is set up in two-dimensional with axis symmetry to unravel the full space dependency of the system. Model definition: the single channel model in analysis of NOx and ammonia conversion kinetics in a dual bed plug flow reactor shows that temperature plays a central role in affecting the optimal dosing of NH3. Because the temperature distribution is sure to vary from channel to channel in monolith reactor, a space-dependent model is called for. Model geometry. The model reactor consists of a model shell that protects and insulates the two catalysts placed inside. Each catalyst bed consists of a monolith support that is loaded with active catalytic material. These two porous domains are modeled as one material. In this model, the catalysts are placed in series, wrapped in a porous supportive mat, and contained in a metal can. The supportive mat protects the catalysts from vibrations and holds them in place. Each monolith consists of reactive channels separated by impermeable walls. The first bed in the reactor is 0.4 meter long and the second bed is 0.06 meter long. They are placed with a small gap between. Both beds have a diameter of 0.32 meter. The volt fraction of the catalyst beds are 0.75. A seal is placed at the inlet of the support mat to prevent erosion of the mat as well as bypassing of reactive gas through the mat. This seal is included as a boundary condition during simulation and not a detail in the geometry. The model equation. The present example takes a pseudo-homogeneous approach to model the thousands of channels present in the monolith reactor. No mass is exchanged between channels so each channel is described by one-dimensional mass transport equations. Furthermore, assume fully developed laminar flow in the monolith channel such that the average flow field is proportional to the pressure difference across each bed. The fluid transports mass and energy only in the channel direction. The energy equation describes the temperature of the reacting gas in the channels as well as the conductive heat transfer in the solid parts of the monolith structure. Because the temperature affects not only the reaction kinetics but also the density and the viscosity of the reacting gas. The energy equation is what connects the channels in a reactor structure, turning this into a space-dependent model. Thermodynamic and transport properties. Accurate thermodynamic data is required as input to energy balance equations, both in the plug flow model in this two-dimensional axisymmetric monolith model. In addition to thermodynamic properties, the model equations also require transport properties to accurately describe the space-dependent reactor model. For instance, the mass transporter needs a specific diffusion coefficients as inputs. The thermodynamic feature provides all necessary properties for the simulation. Different models are available for calculation of thermal and transport properties, thermodynamic models, and the theory. The viscosity of the system is calculated based on the Bruchau model. The thermal conductivity and diffusivity are calculated from kinetic theory and Shetler-Giddings respectively. In this model, to simplify the problem, nitrogen is modeled as a solvent. This means that the gas properties are not composition dependent. Another way to speed up the calculations also used in this model is to use generate material from thermodynamics. Information about how to efficiently use the thermodynamics feature is available at using thermodynamic properties, and the system conditions used in this model are the same as those in the single channel plug flow system. Describe the analysis of nitrous oxide and ammonia conversion kinetics in a dual bed plug flow reactor. Three engine load cases are investigated with a fixed ammonia to nitrous oxide ratio, and the three engine load cases result in the following inlet gas conditions. This simulation shows the molar fraction of NH3, NO, and NO2 in the two catalyst beds for the low engine load case. The effect of the radial temperature gradient is clearly visible as the conversion decreases close to the edge. The temperature for the low engine load case is below the optimal temperature for the SCR reactor, and this figure in this simulation illustrates the result for the intermediate engine load case. As this increased temperature, the conversion increases in the reactor. Higher mass flow rate and higher heat source due to increased conversion gives a smaller radial temperature gradient. The radial temperature gradient has less influence at increased space velocities. For the highest load case, the radial concentration difference is thus lower due to the high temperature. The activity of both beds are high. This results in the lowest ammonia emission among the three cases during oxidation of ammonia in the ASC. The size reaction produces NOx, resulting in a lower NOx conversion than for the intermediate load case. At high engine loads, the ammonia to NOx ratio should probably be lower than for the intermediate load. The effect of temperature on conversion is seen here. In this figure, the conversion is plotted both along the central symmetry axis and along the edges of the monoliths. For a high engine load, the conversion doesn't vary significantly with the position in the reactor, but for lower engine loads, the conversion differs significantly. The temperature differences along the reactor axis at the center of the reactor and at the edge of the beds are seen here in this simulation. Close to the inlet of the first bed, the temperature increases both at the center and along the SCR edge. This is due to the exothermic reactions. After the first rapid temperature increase, the increase in the temperature is slower, and at the edge of the first bed, the temperature instead decreases due to the heat flux to the surroundings. For the high and intermediate engine load cases, the slip of ammonia from the first bed creates a significant temperature increase when this ammonia is oxidized in the second bed. For the low engine case, the activity is too low to create a temperature increase at the bed edge. The heat flux to the surrounding decreases the temperature in the first bed, decreasing the ammonia conversion rate, which creates an even larger temperature increase during ammonia oxidation in the second bed. Finally, the average values of ammonia and nitrous oxide molar fraction were derived both along the outlet of the first bed as well as along the outlet of the second bed. From the results in this simulation, it is clear that for an ammonia to nitrous oxide ratio of 1.3, the exhaust gases from the truck will contain the least ammonia at high load and the least nitrous oxide at intermediate load. With this model, we have shown that in order get low exhaust levels for both ammonia and nitrous oxide, the injected amount of ammonia needs to be adjusted as a function of engine load, and this value has been shown here in this simulation. On the use of dual cell density monoliths. Monolith type substrates are extensively used in automotive catalytic converters and have gained popularity in several other industrial processes despite their advantages over traditional unstructured catalysts such as large surface area and low pressure drop. Novel monolith configurations have not been investigated in depth. In the simulation, we use a detailed computational model at the reactor scale which considers entrance length, turbulence dissipation, and internal diffusion limitations. To investigate the impact of using a dual cell substrate on conversion efficiency, pressure drop, and fluid distribution, the substrate is divided into two concentric regions. One is at its core and one at its periphery, and a different cell density is given to each part. According to the results, a difference of 40% in apparent permeability is sufficient to lead to a large flow mass distribution, which impacts conversion efficiency and pressure drop. The two mentioned variables show a positive or negative correlation depending on what parts of substrate core ring has the highest permeability. These and other results contribute relevant evidence for further monolith optimization. The catalytic converter forms the basis of automotive exhaust gas after treatment system used on most passenger vehicles in Europe, North America, and other regions to control emissions such as carbon monoxide, hydrocarbons, and oxides of nitrogen. Although the catalyst formulation varies depending on the mode of engine operation, the heart of the catalytic converters is multi-channel honeycomb monolithic substrate, the walls of which are covered with the catalytic washcloth. The monolith substrate can be made from either metal or extruded coordinates. Here we limit the discussion to the more common coordinate versions. Furthermore, we discuss the straight-through design and not the type used in wall flow filters. This type of substrate has proven to be convenient in many industrial processes such as carbon dioxide hydrogenation, monopropellant thrusters, and pharmacology synthesis. For some years, there has been an interesting discussion about the role of structured catalyst supports in the next generation of optimized substrates, where three-dimensional printing and computational models are used as ideal tools to explore innovative substrate configurations. Clearly, the catalyst activity is of paramount importance and plays a key role in conversion efficiency. However, the form of substrate is equally important. There are essentially three physical quantities that among them allow a complete description of the resulting converter. These are the cell's density, the wall thickness, and the washout loading. The cell density is the measure of the number of channels that are present per unit frontal area, typically reported in cells per square inch. The first automotive converters typically had 400 CPSI, but in the past two decades or so, there has been interest in monoliths with higher cell densities of 600 or 900 CPSI. The nominal wall thickness is traditionally reported in thousands of an inch, with a standard value being 6.5. Improved technology has allowed 14 about 4.3 mil and ultra thin about 2.5 mil walls. Monoliths with a higher cell density typically have thinner walls. The washcut typically occupies about 12% by volume of the monolith. The cell density and wall thickness dictate the channel size, which combined with the washcut loading govern the open frontal area, which is equal to the monolith porosity. Desirable properties of catalytic converter include fast thermal response to give a short light off time, which implies to a low thermal mass, Thin wall monoliths generally have a lower bulk density and hence a lower thermal mass. Moreover, a loud pressure drop is advantageous because it reduces fuel consumption. Pressure drop depends on both the OFR and the channel size, with larger channels giving a lower pressure drop. Further related to the channel size is the average washout thickness as well as the external surface area of the washout that is exposed to the gas. These factors can both affect the conversion obtained. The use of an inlet diffuser combined with external heat losses from the converter gives rise to non-uniform radial velocity and temperature profiles in the monolith. The fluid distribution in monolith type converters has been extensively studied over the past several decades, both experimentally and using computational modeling with various geometries and transient conditions. Some studies have specifically looked at the effect of fluid distribution on the light of performance. Other studies have modeled efforts to alter the fluid distribution using fluid tailoring devices. As high cell density monoliths tends to have a lower thermal mass, their use has been proposed to reduce the light of time. When cell density is changed, a number of other properties, including the fluid distribution, are also affected. So it is necessary to include all of these effects in a model. Another idea that has been proposed is used to composite monoliths composed of rings of various cells densities to improve the light of performance. The effect of such a design was briefly explored, and who showed the combining 400 and 900 CPSI cell density substrates reduced the light of performance compared to the use of single cell density. In view of the literature extant on the subject of the effect of fluid distribution and cell density on the light of performance and recent commercial developments. This simulation presents a computational study of the effects of using dual cell density structures in monolith catalytic converters. The effects of such structures on the velocity and temperature distributions and subsequently on the chemical conversion is demonstrated for a variety of dual cell configurations. The sectional computational model. This section describes the computational model implemented. A description of the domain. The domain tested was a catalytic converter similar to those tested in experimental rigs. That is an inlet pipe, in this case 1000 millimeter long and 27 millimeter in diameter, followed by a 67 millimeter long diffuser connecting the pipe with a monolith 152 millimeter long and 60 millimeter in diameter. The outlet cone was replaced by a straight pipe of the same diameter as the monolith and 30 millimeter long, which has a marginal effect upwind of the domain and makes it easier to register the radial profiles of the variables of interest at the outlet of the substrate. The monolith was assumed to have square cross-section channels and be made of coordinate with a coordinate porosity of 30%. The idea was to compare homogeneous and heterogeneous cell density monoliths. Hence, the zone of the substrate was divided into two concentric regions, one at the center referred to as the core, the other at the periphery referred to as the ring. And this simulation shows such a domain where one half of the transverse areas was given to the core and the others to the ring. This section summarizes the results obtained. The four combinations listed here in the simulation were investigated. First, we analyzed in detail the cases where the core and ring had the same volume. Then, we report a brief parametric study where the size of the core increased progressively. The chapter of evenly distributed dual cell density. This simulation shows the velocity over the domain for four cases. In the two of the cases, A and C, the ring and core had the same cell density. In those cases, the fluid distribution was fairly homogeneous and similar between them, as can be seen in this velocity profile at the exit phase of the substrate in this figure. On the other hand, for cases B and D, where the core and ring had different cell densities, the fluid distribution was largely affected by the combination of the cell densities. The role of the diffuser is to spread the flume more uniformly across the face of the monolith. However, usually the majority of the fluid remains concentrated in the central section. Therefore, one might expect that, regardless of the cell densities, used, the bulk of the fluid might pass through the central zone. However, we observe the different behavior. Indeed, the fluid pattern in the diffuser has only a minor effect on the fluid distribution when dual zone monoliths are used. The main factor that determines the fluid distribution in this case is the difference in the viscous resistance of the two monolith regions. This can be observed in this simulation. Comparing the permeability of the ring and core monoliths is indirect because the flow model considers the hydraulic entrance length. However, a quick inspection can be performed by analyzing the asymptotic friction factors in the fully developed region, that is, by comparing factor uh, Vm to the Hm of both monoliths. According to the data in this simulation, the apparent permeability of the 900 per 2.5 monoliths is only 40% lower than that of the 400 per 6.5 one. However, such a difference is sufficient to impact significantly the fluid distribution. It should be pointed out that there have been several efforts on improving the fluid distribution inside a catalytic converter by adding diffuser elements, changing the inlet cone, and similar solutions. But using an optimized combination of cell densities, washout loading, and so on has not been explored extensively yet. The temperature distribution was also analyzed. According to the results in this simulation, the temperature fields of the four cases are similar. Since heat is transferred to the exterior through the carcass, the ring monolith is expected to have a lower temperature than in the core. Let us call the hot region the zone with temperature above 500 Kelvin. A slight differences can be seen when the core monolith is 900 per 2.51, where the hot region covers almost the whole core. At the same time, the cases with a 400 per 6.5 monoliths in the core and had a lower average temperature. The change in the temperature between the core and ring zones may have an impact on the fluid distribution given the change in density. However, according to this simulation, the computed fluid has a strong preference for the zone with the lowest cell count regardless of the temperature. Despite the cell density of the ring monolith, the two cases with the 900 per 2.5 monolith in the core show higher temperatures than those with a core of 400 per 6.5. The thermal conductivity of the 400 per 6.5 substrate is approximately 30% higher than that of the 900 per 2.5 substrate. Hence, a more homogeneous temperature would be expected in that region. It is also important to mention that both substrates differ in their void fraction but have the same 12% by volume of washout. Consequently, the washout represents a higher percentage of the solid volume in the 900 per 2.5 monolith than in the 400 per 6.5, and this difference is in washout fraction changes not only the thermal conductivity but also the thermal mass of the reactor. Therefore, it may have an impact on the light of care. Due to the many variables involved in this process, analyzing the light of is beyond the scope of this work, but will be addressed in the future simulations. This simulation shows carbon monoxide conversion for comparison purposes. Local values of carbon dioxide conversion were calculated. It should be clarified that the values in the simulation were computed are the inlet and local CO mass fraction of carbon monoxide respectively. In none of the cases analyzed was full depletion of CO reached. However, there are significant differences that are worth mentioning. First, full depletion of the CO was reached in the two substrates with a 900 per 2.5 monoliths in the core, on the other hand, independent from the position, covering the parts of the substrate with 400 per 6.5 monolith didn't reach 100% conversion. A 900 per 2.5 monolith has a higher geometric surface area than a 400 per 6.5 monolith. However, the same volume percentage of washout was given to both monoliths and hence the same amount of catalyst, so the latter was discarded as a possible explanation of the differences. Regarding the temperature, CO in the feed is fairly diluted, so the heat released from the chemical reaction didn't drive significant changes in the temperature field. The results may differ in other scenarios where the thermal effects of the chemical reactions are significant. What should be taken into account is that the surface velocity is higher in the 400 per 6.5 substrate than in the 900 per 4.5, that is a lower space-time. According to the data in the simulation, the increase in space velocity when entering the substrate is 1.16 times higher in the 400 per 6.5 monolith than in the 900 per 2.51. Although this change is small, together with the inlet velocity, it led to a channel apparent velocity in the 400 per 6.5 monolith almost twice higher than that in the 900 per 6.5 monolith, such as a combination of the factors is quite consistent with the result here in the simulation, and this simulation shows the reaction rate for the four combinations of ring and core monoliths where both had the same volume. The profiles are consistent with the results in the simulation. In the core region, the reaction rate starts high, then it progressively decreases until full depletion of CO. It can be seen from equation that the denominator in the rate expression is close to the 1, and also that given the inlet composition YO is almost constant. Hence, the main factors driving the reaction rate are temperature and YCO. According to this simulation, the former is comparable in the four cases, so the latter dominated the reaction rate among all of the other parameters in the rate expression. NM requires further attention. According to the data in this simulation, the characteristics of washout length in the 400 per 6.5 monolith is almost 49% longer than the one in the 900 per 2.5 configuration. The impacts in the Tele modules, however, according to the local values observed in the results, it didn't lead to significant differences in the effectiveness factor in this section. The results are extended to the cases where the percentages of the transverse area given to the core and ring monolith were not even. Instead, the relative size of the core increased progressively in steps of 10% from 0% to 100%, and this simulation shows the fraction of the fluid passing through the core monoliths in the case where a 900 per 2.5 core was inserted in a 400 per 6.5 monolith and vice versa. It can be seen that the relationship is superlinear when the core had a 400 per 6.5 monolith and sublinear when the ring corresponded to a 400 per 6.5 monolith. It should be noticed that the curves are not reciprocal between them, looking at two cases where 50% of the flow area corresponded to the core. When the 400 per 6.5 monolith was placed at the core, approximately 60% of the flow passed through it. On the other hand, for the opposite case, where the 400 per 6.5 was placed at the ring and covering the same 50% of the transverse area, only the 36% of the fluid passed through the section. Such a value is lower than the 40% expected if the curves were the exact reciprocal. This asymmetry may come from the fact that the fluid approach the substrate mainly to the center of the converter. However, there was still a marked preference of the flue for passing through the monolith that imposes the lowest viscous resistance despite its location. Regarding back pressure, in this simulation shows its sensitivity to the size of the core. The relationship between the variables is slightly nonlinear. It is somehow striking that the two cases with the evenly distributed flue areas led to an almost identical pressure drop regardless of the placement of the monolith with the highest and lowest cell density core or ring. This result was not reproduced when analyzing the sensitivity of CO conversion, where both trend lines 400 per 6.5 and 900 per 2.5 in the core behave differently, as shown in this simulation. When a 900 per 2.5 core was inserted in a 400 per 6.5 monolith, the conversion curve showed an approximate U shape. There is a minimum of CO conversion when the core monolith had approximately 1 per 3 the volume of the catalytic zone. Such a combination led to a conversion even lower than that when the whole catalytic zone was made of a 400 per 6.5 monolith. Consistent with this limit simulation, a relatively small core with a higher viscous resistance deviates to the ring an amount of fluid that is higher than the proportional one, decreasing even more the spacetime of the peripheral channels and damaging the overall conversion. At a core size of 50%, the conversion reached the same value obtained when using a flat 400 per 6.5 monolith. From that point, conversion increased practically linearly with the core size. In the opposite case, where the core of 400 per 6.5 was embedded in a 900 per 2.5 monolith, conversion decreased noticeably with each increase of the size of the core. That is also explained by the preference of the flue for the zone with the lowest back pressure. Despite its size, this agrees with the results in the simulation for the 400 C per 900 R combination, which show a sublinear relationship between the size of the core and the proportion of the fluid passing through it. And what is about the conclusion? The fluid patterns in the dual cell density monoliths was successfully analyzed. The main conclusion from the simulation is that a monolith with mixture of the two cell densities can in fact lead to a better or worse result than that from using either of the two cells density individually. It is reasonable to expect that a result from using a combination of two cell densities would be obtained from the interpolation of the results from both cell densities individually. However, the simulation has demonstrated with a theoretical model that a combination of cell densities in a single monolith can lead to a conversion efficiency lower than that obtained when using any of two cell densities alone. Let us refer to that as unbounded efficiency. The aforementioned result can be considered a negative one since what is desired is a higher conversion efficiency. Nevertheless, it shows that unbounded efficiencies are possible when combining cell densities. Positive results are also observed. We remark specifically on the case when the core and ring have the same volume. The two combinations 900 C per 400 R and 400 C per 900 R lead to the same pressure drop, but in the latter combination the CO depletion is 50% higher. This improved trade-off between back pressure and conversion efficiency shows the potential for monolith shape optimization by using heterogeneous cell densities. The most notorious and direct effect of using a heterogeneous cell density was a largely uneven fluid distribution. The fluid strongly prefers passing through the section with the lowest back pressure regardless of its placement, core or ring, or periphery of substrate. In this paper and simulation, the two cell densities used differed by approximately 40% in their apparent permeability, which is sufficient to impact significantly the fluid distribution. It is recommended to explore other combinations with a more similar apparent permeability by varying the channel size, wall thickness, or amount of washout. There were only minor effects on the temperature distribution despite the differences in the effective thermal conductivity and rate of conversion between the core and ring. However, the cases analyzed considered the steady-state regime and with the reactants fairly diluted in the feed. Significant effects may appear in the transient operation or if the reactants are sufficiently concentrated to produce a significant release of heat from the chemical reactions. Those situations should be investigated. Conversion efficiency is also affected by the cell density distribution of substrate. This effect is highly correlated to the fluid distribution among the cases analyzed. It is found that a relatively small core inserted in a monolith with a lower viscous resistance increases the pressure drop and decreases conversion efficiency simultaneously. Hence, such a combination is highly discouraged. On the other hand, if the core has the lowest viscous resistance, then the pressure drop and conversion show a positive correlation. Analysis of the effect of substrate material on the steady state and transient performance of monolith reactors. We studied the effect of the substrate material ceramic versus metallic on the steady state and transient performance of monolithic reactors using a one-dimensional two-phase model with a position-dependent transfer coefficients. When the operation of the reactor is on the ignited branch, it is shown that the monoliths with metallic substrate clearly lead to a superior steady-state performance compared to those with ceramic substrate. In such cases, the ignited branch extends to lower inlet gas temperature, typically between 60 to 100 degrees of centigrade in after-treatment applications. For the same catalyst loading. For transient operation where the time to light off is important, it is shown that for for the case of back-end ignition corresponding to low inlet temperatures or low catalyst loading. Metallic substrates are again superior, however, for the case of front-end ignition, ceramic converts may lead to lower cumulative emissions at lower inlet gas velocities, while the converse is true at higher velocities. It is shown that the transit heating time and hence the cumulative emissions decrease with decreases in the channel hydraulic diameter and thermal capacitance of the substrate, but are not monolithic with the inlet gas velocity. We present mathematical analysis and simulations to support this conclusion. Some novel results on the effect of substrate conductivity on the number of states and opposite propagation of temperature fronts are also presented. Monoliths consist of honeycomb structures with large number of straight parallel channels of a small diameter between 0.5 to 6 mm through which the fluid flows. Catalyst monoliths are widely used in pollution abatement such as the oxidation of CO and unburned hydrocarbons and reduction of NOx from gasoline and diesel engines, and in the combustion of VOCs in the chemical industries. Due to their several advantages compared to the pellet type reactors, monoliths are exclusively used in the exhaust after treatment of the automobiles. For example, three-phase converters, TWCs, diesel oxidation catalysts, DOCs, and lean NOx traps, LNTs, and selective catalytic reduction units, SCRs. The substrate of the monoliths used in the automobiles is mainly made up of corrugates, which has lower thermal conductivity between zero point 0.8 to 2 watt per meter Kelvin. However, metallic monoliths are gaining wider use in recent years. In the TWC, nearly between 60 to 85% of the cumulative emissions are before the converter lifetime, which takes about between 10 to 18 per seconds, depending on the catalytic's loading, location, and other factors. This length of time also depends on the thermal capacitance of the converter and the exhaust gas temperature and the velocity at the inlet of the converter. Metallic substrates have a higher heat capacity compared to the ceramic for the same volume, but the total thermal capacitance of the metallic monolith may be comparable or lower compared to the ceramic monoliths due to the thin walls. While high substrate conductivity leads to superior steady-state performance, it may lead to the longer transient times. Thus, the effect of the substrate material on the overall performance of a monolith is not clear. There are few studies, mostly experimental, in the literature comparing the performance of ceramic and metallic monoliths. We review here briefly the literature related to this topic. Nishizua and his colleagues in 1989 found that the conversion efficiency of the metallic converter is better than that of ceramic converter of equal cell density. In contrast, Jasper and his colleagues in 1991 reached the opposite conclusion, while the Peplis Graf and his colleagues in 1996 concluded that the type of substrate doesn't significantly affect the conversion efficiency of the converter. Panon and Muller in 2001 compared the ceramic and metallic converters with the same volume and cell density and concluded that the ceramic substrate has superior conversion efficiency relative to the equivalent cell density metallic substrate of the either equal volume or equivalent surface area. Santos and Costa in 2008 compared the performance of the ceramic and the metallic converters for several vehicle operation conditions. They concluded that the ceramic substrate perform better compared to a metallic at low space velocities and vice versa for higher space velocities. From these few studies in the literature, it is clear that there is no general agreement among the authors about the effects of the substrate material on the converter performance. We also note that there are a few modeling studies comparing the effect of the substrate material on the CDSA and transient performance of monoliths. Rimanotto and his colleagues in 2004 examined the effects of the solid conduction on the hysteresis locus and showed that the precious platinum group metal PGM loading need to obtain light of in a metallic monolith is about a factor of 10 times smaller compared to a ceramic monolith with all other parameters fixed. In a separate study, Ramanand and his colleagues in 2004 also presented simulations of the transit behavior and showed that for the case of back-end ignition, the cumulative emissions may be lower for metallic monoliths. However, for the case of front-end ignition, the lifetime is shorter for ceramic monoliths, leading to lower cumulative emissions compared to metallic monoliths. These, as well as other prior modeling studies in the literature, were mainly concerned with emissions from automobiles. Recently, there is also interest in using monoliths in catalytic combustion partial oxidations, as well as other heterogeneous catalysis applications in place of conventional reactors like packed beds. For example, in recent works, Mostri and his colleagues in 2005 compared various supports, monolith forms, and packed beds for the conversion of the methan's syngas by partial oxidation. In such cases, the transit usually plays a minor role compared to the steady-state performance. The main goal of this work is to analyze in some detail the impact of the substrate material on the steady-state and transit behavior on the monolith reactors used in their after treatment, as well as other applications cited above. Some simulation is organized as follows. In the next section, we present a one-dimensional two-phase model of the monolith reactor with position-dependent transfer coefficients. Since metallic monoliths used in applications have sinusoidal channels for which the transfer coefficients are not readily available in the literature. We present some computed new results on the asymptotic Nusselt and Sherwood numbers for sinusoidal channels of various aspect ratio. In the next section, we present a detailed analysis of the steady-state behavior of the monolith and the effect of the substrate conductivity on the ignition and extinction points. In the fourth analysis of transit behavior and temperature front propagation, and the next one is analysis of the effect of the substrate on cold start time. We analyze the transit behavior of the monolith and the dependence of the cold start or cumulative emissions on the substrate properties. In this next section and last section, we present numerical simulations that are guided by the analysis. The main results in this work are summarized here. The first one is a mathematical model. We consider a one-dimensional two-phase mathematical model of a straight channel washout catalytics monolith with flowing assumptions. Conduction diffusion in the axial direction is negligible in the fluid phase. The fluid channel is laminar, either fluid developed or developing. The pressure drop in the channel is small so that its effect on the concentration and velocity may be neglected. Constant physical properties, uniform channel cross-section, and the chapter steady-state bifurcation diagram. Before we present numerical simulations, we analyze the effect of the solid conduction on the steady-state behavior of the monolith using simplified versions of the above general model. We consider first the limiting case of the zero solid conduction and uniform catalyst activity. Further, we make the assumption of constant values for the transport coefficient. Asymptotic values for the transport coefficients. Use a positive exponential approximation and neglect washout diffusion limitations with this assumption. Analysis of transit behavior and temperature front propagation. In this section, we review the conditions for back-end and front ignition in monolithics and analyze the impact of conduction in the substrate material on the temperature front propagation. Analysis of the effect of substrate and cold start time. We now present a brief analysis of the effect of the substrate materials on the cold start or heating time. As stated earlier, the substrate material can influence light of time in two ways: through the solid conduction and propagation of the temperature front through solid heat capacitance. The reduction in the substrate wall thickness reduces the thermal capacitance but also increases the heat Piclet number as shown above. For the case of the back-end ignition, the lighter front may not. And the chapter of numerical simulation results on the effect of the substrate material on cumulative emissions. In this section, we present numerical results that validate the analysis of the various sections. The values of the various parameters used in the numerical simulations are given here. In this simulation, as stated earlier, these values are typical in the after-treatment applications. Before presenting the simulations, it should be pointed out that monoliths with ceramic substrate come with different channel shapes, with majority being at the square, whereas metallic monoliths are usually made of different shapes and material. And conclusion and discussion. As stated in the introduction, the main goal of this work was to investigate the effect of the substrate material on the steady state and dynamic behavior of the catalyst monoliths. If the objective is to operate the monoliths in the region of multiple steady states and on the ignited branch, then we have shown that monoliths with high conductivity substrates, metallic and or high aspect ratio diameter to length, lead to the ignited branch at lower inlet gas temperature, typically between 60 to 100 degrees of centigrade. And the background. The modern reactor consists of a metal shell that protects and insulates the two catalysts placed inside. Each catalyst bed consists of a monolithic support that is loaded with a active catalytic material. These two porous domains are modeled as one material. In this model, the catalysts are placed in series, wrapped in a porous supportive mat and contained in a metal can. The supportive mat protects the catalyst from vibrations and holds them in place. Each monolith consists of reactive channels separated by impermeable walls. The first bed in the reactor is 0.4 meter long and the second bed is 0.06 meter long. They are placed with a small gap between. Both beds have a diameter of 0.32 meter. The void fraction of the catalyst beds are 0.75. A seal is placed at the inlet of the support mat to prevent erosion of the mat as well as bypassing of the reactive gas to the mat. This seal is included as a boundary condition during simulation and not a detail in the geometry. The exhaust gas passes through the channels in the monolithic beds in the reactor. And the modern definition: the reactor is symmetric in its design, which gives the geometry seen in the right figure, and symmetry reduces the modeling domain. A result of nitric oxide and ammonia conversion in a dual bed monolith reactors. Conversion kinetics in a dual bed plug flow reactor. The flow temperature results in loud conversion of both nitric oxide and ammonia. Molar fraction of ammonia, nitrogen monoxide, and nitrogen dioxide in the reactor. Low engine load and NH3NOx equals to 1.3 fluid flow from top to the bottom. Thank you so much for watching my tutorial video until the end, and also you can download this Comsol simulation from github.com/mahsa script.